So, welcome to our lecture where we are going to be going over correlations and t-tests. So, first, we're going to talk about the basic idea behind correlations and t-tests, and then we're going to shift over into how to do them in Excel. So, correlations specifically, it's going to give you a Pearson correlation coefficient, or Pearson's R. And this is going to range from -1 to 1. And this is used when you have two continuous variables. So if you're looking at something like age and SAT score, or income and wealth, right? Those are continuous variables. Now, you are going to have, like, if we're talking about it ranging from -1 to 1, if you had a correlation coefficient of 1, that would mean a perfect correlation. That means that all of the dots on your scatter plot lined up perfectly on a line. And the correlation coefficient, again, would be 1. That being said, you're never really going to see a correlation coefficient be 1 in the real world because nothing is really perfectly correlated, at least in the social sciences. Alternatively, you might have a negative correlation coefficient, one that is -1. If it is a -1, that means that there is a perfect negative correlation. It means that all of those dots on your scatter plot would be perfectly lined up in a line going down. So where one of your variables, your x variable maybe goes up and your y variable goes down. Or alternatively, your x variable goes down and your y variable goes up. By contrast, a positive correlation of 1 means that both of them are going up together. Both of them are increasing together. But really, you are not going to see a correlation coefficient of -1 or 1. If you do, you should let me know because that would be really weird. Most of the time, what you're going to see is correlation coefficients in the 0 to 0.5 range, right? And 0 means that there is no correlation between the two, right? 0 means that there is no correlation between the two. But most of what you're going to see are these values that range from like 0 to 0.5, and we'll look at an example today. So here is in a Pearson's R, a correlation coefficient of 0.37. So I would probably describe this as a weak to moderate positive correlation. And you can see in the data that it's sort of scattered about, but there is a positive cloud to it where you can see that as your x variable increases, so on average does your y variable. Here is another example. This is a slightly tighter cloud, and really if you saw a correlation of 1, you would see all of these lines, all of these dots lined up on a line. They would be perfectly correlated. But most of the time what you see in your scatter plot is a bit of a cloud, right? But this cloud has a bit of shape to where you can see that as your x is increasing, it also looks as if your y is increasing. And the correlation coefficient here is 0.66. So if we went back to our first example, this is sort of a looser cloud, which is why you see a lower correlation coefficient. It's closer to 0, meaning there's less of a correlation between the two. Whereas here is a much tighter cloud because that correlation coefficient is higher, right? There's a higher correlation between our x and our y. This is our third example with a correlation coefficient of 0.79. And you can see, even compared to our second example, it is a tighter cloud. This is a tighter cloud than our first and second example. And you can see that that correlation coefficient is going up, right? It's getting closer to 1. And we would describe this as a strong positive correlation. This is a strong positive correlation. This last one, example 2, was maybe a little bit closer to a moderate correlation. This is a strong positive correlation. And then finally, this one is much more of a cloud. Like, do you see necessarily a clear trend here? No, this one has a correlation coefficient of 0.25. That's still like a weak Positive correlation is probably how I would describe this, as a weak positive correlation if it's around 0.2. But there doesn't seem to be necessarily a clear trend line like where we saw this one. It's very obvious that you could draw a line through this, that it's a strong positive correlation. All of these observations are tightly clustered, whereas this is just like a giant cloud. And the more your scatter plot looks like a cloud, the more likely it is that you have a correlation coefficient of 0 or something close to 0, which means that you have no correlation. Now, the other test that we have is a t-test. So a t-test is where you are comparing the means of two groups when you have a binary categorical variable and one continuous or ordinal variable. So for instance, let's say we are comparing the incomes of men and women, right? That is a binary categorical variable, men and women. That's a categorical variable, gender, and then it takes on values of 0 or 1, right? Man or woman. Binary meaning it takes on two categories, okay? And then you have a continuous variable or ordinal variable like income. And let's say in our sample, we see that men make 105,000 and women make 100,000. But is there a statistically significant difference there? Is that difference large enough? You probably couldn't guess based off of your own intuition. Instead, we have to rely on statistical tests, and they can tell you if there's a statistically significant difference in those two groups' incomes, okay? Now, ultimately, this is going to tell us, again, whether there is a statistically significant difference between these two groups, okay? And I'll talk about interpretation in a second, but what it inherently does is it looks at the difference in distributions between two groups. So let's pretend that these are men and these are women. Men are making 105,000, women are making 100,000, and this is their average income here, men making 105, women making 100, and this is their distribution around their mean, with these dashed lines being their means. And this statistical test, looking at the distribution of data and looking at the means, can tell us whether these numbers are different enough to be able to say there's a statistically significant difference between these two means. So I want to just break to Excel to quickly show you how to do this on your own. So here is our data set. And the first thing that we are going to be looking at, this is just our same example data set from earlier, from our first example of figures. And what we can see here is south, that's a binary variable, 0 or 1. And then we have two continuous variables, percent pro-choice and percent Romney. And let's say that I have a hypothesis where I say there is a statistically significant difference between southern and non-southern states regarding vote share for Romney in the 2012 election. Specifically, I think that Romney is going to perform better in southern states than non-southern states. I think that is probably pretty intuitive. But how would I do this? How would I compare southern states to non-southern states in their vote share? First, what I need to do is I need to sort south, which is my binary categorical variable, and I go to south, click on all of these, do data, filter, hop down to south, and say sort ascending. Sort ascending, just to make sure that all of my southern states are together and all of my non-southern states are together. And here you can see I've grouped all of my southern states together and I have all of my non-southern states grouped together. And I'm going to use the following formula. I'm going to say equals, and that's always how you start formulas in Excel, equals. It tells it, hey, I'm about to have a formula or a math, some kind of math calculation. But this time it's formula, and I'm going to say equals T dot test. And then I'm going to say open parentheses. And rather than highlighting the southern values over here, I'm going to highlight % Romney for non-southern states first. All the way down, you can see, look, I went all the way down to my last non-southern state, Utah. And then I'm going to say comma. And then I'm going to highlight all of the values of % Romney for my southern states. So you can see up here in this formula right now I have equals T dot test, open parentheses, and then I highlighted vote shares for all non-southern states, comma, then all southern states. And then the next part, I want you to default to a two-tailed distribution, 2. You can learn about this a bit more in 336, but just trust me, you want a two-tailed distribution for this test. And then we're going to say comma again. We want to do a 2-sample equal variance test. So 2, 2. And then I'm going to close parentheses. Okay. Now here it gave us a value of 0.00189. Now you are going to get output here that ranges from 0 to 1. And if it is less than 0.05, it means that there is a statistically significant difference between your two groups. So is this less than 0.05? Yes. Is this value my p-value, which is what this is called, less than 0.05? Yes. So here I would say my p-value is 0.00189, which is less than 0.05. This means there is a statistically significant difference between southern and non-southern states regarding their vote share for Romney in 2012. In other words, this means that southern states voted in more support for Romney than non-southern states, right? That they did vote, southern and non-southern states did vote differently here, okay? That is the underlying finding, that there is a statistically significant difference between southern and non-southern states regarding their vote share for Romney in the 2012 election. So this gave us a p-value. Now the correlation test is, I'll just make a note here, this is a t-test, and just bold it, okay? Next up is correlation, okay? Now you don't need to worry for this one about sorting any variables first. Remember with our t-test, we had to sort by southern and then compare the average % for Romney and in non-southern states and the average % for Romney in southern states, but we had to sort by south first. You don't need to sort when you are doing correlation, okay? You don't need to sort if you're doing correlation. Now, correlation is a slightly more straightforward test. The first thing that you're going to do is say equals correl, open parentheses. I have to do it again in all caps just so you can maybe see it a little bit better. Equals correl, short for correlation, I bet you guessed. And we're going to open parentheses and we're going to highlight all of the values from our first variable, okay? All the way down. Please note, I did not highlight the text at the top. I only highlighted the numeric values, okay? So I highlighted from D2 to D51, okay? That's my first variable. So you're going to put your first variable in. It doesn't matter if you do your independent or your dependent variable first. The outcome, the output that it's going to give you is the same. Now the next, I'm going to do comma. So comma, and then I'm going to highlight my second variable's values. So let's say that I was interested in seeing whether pro-choice attitudes are correlated with vote share for Romney. Now I'm going to highlight vote share for Romney all the way down. So you can see I highlighted my first variable, then I highlighted my second variable, I highlighted my independent variable, then I highlighted my dependent variable, and then I'm going to close parentheses. And this is a pretty strong negative correlation. So just like we talked about in the video lecture, you're going to get output that ranges from 1 to -1. So if it's close to 0, it means there is no correlation. If it is close to 1, it means the two variables have a strong positive correlation. If it's close to -1, it means the two variables have a strong negative correlation. So here I would probably say the correlation coefficient is -0.76, which means there is a strong negative correlation between percent pro-choice and vote share for Romney. In other words, as a state becomes more supportive of women's abortion rights, a state becomes less likely to support Romney. But you are gonna get, and I've made a little worksheet too that you can look at in association with this video lecture. But if you get something that's close to 1, that, I'll say close to 1 because you're definitely not getting a 1. You have a strong positive correlation. If you get something that's close to 0, that's no correlation. If you get something that's close to -1, that's a strong negative correlation. If you get something that's close to -0.5, or excuse me, to 0.5, I would say you have a moderate positive correlation. If you get something that's close to 0.2, we would say weak positive correlation. If you get something that's close to -0.5, you have a, well, I'm going to put it here, -0.5. We would say a moderate negative correlation. And then finally, if you have a -0.2, you have a weak negative correlation. Now, just as an FYI, like this might be a little bit like confusing currently, but I want you to attempt it on your own. And we can talk about if it didn't work or interpretation or any of that next week when you meet with me about what results you currently have. But this is just sort of a general outline and guideline for how you can interpret these results, okay? If you have any questions about any of this, I'm going to post this data along with a worksheet, this one, in association with this lecture, so you can go to either of them to get a bit of help. But if you need help with anything, please feel free to reach out. Otherwise, I'll see you at our meeting next week.